When we think about the ocean fighting climate change, our minds usually go to things like plants and whales. But what if I told you the ocean has a much older, much slower, and way more permanent solution? We're talking about a powerful, ancient process that literally turns carbon dioxide from the air into solid rock. Yeah, you heard that right, rock. It locks it away for millions of years. So let's dive into this incredible story of Earth's own geological carbon capture system.
So, here's our game plan. We're going to start by uncovering the ocean's big secret. Then, we'll follow carbon as it makes this wild transformation from a gas into a shell. We'll take a deep dive on its journey to the bottom of the sea, see how it gets locked away in a kind of million-year prison, and finally, and this is a big one, we'll look at why this whole amazing system is now at risk.
All right, let's kick things off with Section 1, the ocean's deep carbon secret. We're going beyond the usual suspects here, beyond the biological cycles you might have heard of, to explore a much slower but incredibly powerful inorganic pump. And this, right here, is the central question for our entire explainer. How does the ocean turn air into solid rock? It sounds like something out of a sci-fi movie, doesn't it? But it is a real planetary-scale process that has been balancing our climate for eons. And trust me, the answer is absolutely fascinating.
Okay, so first things first, let's get one thing straight. Most of us have probably heard of the biological pump. That's all about living things, right? Phytoplankton sucking up CO2, then dying and sinking. That's all organic carbon. What we're focusing on today is its less famous but just as important cousin, the carbonate pump. And this one deals with inorganic carbon. We're talking minerals.
So, how does this whole thing actually kick off? Well, that takes us to Section 2, from gas to shell. This is where the magic really starts to happen, thanks to a perfect team-up between ocean chemistry and marine life.
It pretty much boils down to 3 key steps. First, CO2 just naturally dissolves from the air right into the ocean surface. Easy enough. Then, that dissolved CO2 reacts with the seawater and creates something called carbonate ions. You can think of these as microscopic Lego bricks. And then, this is the really cool part, tiny marine organisms grab these little bricks and use them to build their shells. And who are these amazing little architects? They're called calcifying organisms, and we're talking about a huge range of life here, from corals and shellfish all the way down to microscopic plankton. These guys are the real engines of the carbonate pump. They're literally pulling dissolved carbon out of the water and turning it into a solid physical thing. They are nature's tiny rock factories. Okay, so the carbon is now locked up in a shell. Great. But how does it get put away for good? Well, that's where Section 3 comes in, the great downward journey. To really store this carbon long-term, it has to travel all the way from the sunny surface down to the dark, crushing pressure of the seafloor.
I love this quote because it paints such a perfect picture. When these billions of tiny organisms die, their little calcium carbonate shells start to sink. Just try to imagine it, a slow-motion, never-ending snowstorm made of chalk, just gently falling through miles of water, carrying all that carbon down into the abyss.
And this whole process has a name, of course, sedimentation. It's the slow, steady buildup of all these shells on the seafloor. We're talking layer after layer, century after century, forming this massive blanket of stored carbon.
So what happens in the deep ocean is absolutely crucial. This material settles everywhere, building up these incredibly thick layers of sediment. Some of it even finds its way into the deepest places on the entire planet, like the Mariana Trench. And once it's down there, it is completely cut off from the atmosphere, effectively taking that carbon out of the climate system for ages.
And this leads us to the final, amazing transformation in Section 4, carbon's million-year prison. This is where that loose sediment gets locked away permanently by literally becoming solid rock.
This timeline really gives you a sense of the incredible timescale we're dealing with. So after the shells start settling, it might take 100,000 years for the sheer weight of all the layers on top to squeeze everything together. Then, over 1,000,000 years or even more, this compacted stuff cements itself together in a process called lithification. It actually turns into rock. Just take a second and let that number sink in. Millions of years. This isn't some quick fix. This is one of the most permanent carbon storage solutions on the entire planet. That carbon atom that was once floating around in the atmosphere is now a physical part of the Earth's crust.
And what's the end result of all this? You get these massive deposits of rocks, like limestone. You've heard of the White Cliffs of Dover, right? That's the carbonate pump right there in action. These rock formations are one of the biggest single storage tanks for carbon on our whole planet.
all built by tiny little organisms over an immense amount of time.
And all of that brings us to our final and maybe most critical section, a system under threat. How does this ancient, powerful process hold up against the challenges of our modern world? Well, specifically, we need to talk about ocean acidification.
So here's the problem, and it's pretty straightforward. The more CO2 we pump into the atmosphere, the more the ocean soaks up. And when CO2 dissolves in water, it makes that water more acidic. It's a fundamental chemical change, and it's happening on a global scale.
Just take a look at this chart. Ocean acidification directly messes with the availability of those carbonate ions. You know, the Lego bricks we talked about earlier. In an ocean that's more acidic, there are simply fewer of these essential building blocks floating around for marine life to use to build their shells.
And the consequences of that are direct and honestly pretty alarming. With fewer carbonate ions to work with, these shell-building critters struggle. It takes them more energy to build their homes, and their shells can end up thinner and weaker. But here's the real takeaway. This weakens the very first, most critical step of the entire carbonate pump. And if that first step starts to fail, the whole system's ability to lock away carbon for millions of years gets smaller.
And that leaves us with a really big question. The carbonate pump is this ancient, elegant, and incredibly effective system for safeguarding our planet's climate. By changing the ocean's basic chemistry, are we accidentally messing with one of the very systems that has kept Earth stable for millions and millions of years? It's definitely something to think about.